I'm start recording, by the way. Okay, here's the thing. I want to also ask another question. So far, the material that I cover in this course, is it clear or it's not clear? More or less. Okay, so maybe we can stop here. Yeah, Elvis, can you please let me know what is exactly is not clear? Okay, so here, I want to say something, and please, everybody, please, I just don't understand how to even start the program. Okay. So here, what about the rest of the people? I would like to know everybody, a participant at the moment in this lecture, what is clear, what is not clear, so I can just go slowly again. Then, I will move forward to the rest of the material today. Before I start, everybody agree this is a new material, right? This is something you never ever seen, right? So that means, what is the best approach for us to learn is to observe, analysis. Yes.
I think the main thing is just practice mostly.
And then practice, exactly. So it's learn by doing. Basically what I'm doing in front of you is learn by doing. Because, I can give you a very strong theoretical lecture. You guys will not be happy. You know what I mean? My idea that actually, yeah, you're right. It needs to be practice. I just need to go into the Elvis and try to see what is the problem so I can help him as much as I can. So here's the thing. First of all, do you all of you agree that whatever we are doing at the moment is aligned with the 2300, the digital logic design?
Yes.
Exactly. So if you guys know 2300, you're set. Basically, this course is called Verilog, is how to describe your circuit on a chip instead of having a breadboard and you already make a routing and connections and stuff like that. Do you agree? Okay. So if you need to do the following, please go back to your material of the 23, where I get confused. Yes. You need to go back to your material, to the combinational circuit, sequential circuit, digital logic, gates, and read it. Okay, while you are doing this, there is no also shame for you to come and say that, Professor Ali, can you please go through this part in the 2300? I will be more than happy to assist you. The second thing, for everybody attending, you have to know that, there is a skill you're gonna build. So in 2300, you are building demultiplexer, and you are building multiplexer, and then you are building a flip-flop, or you're building something, right? Those are pieces. Now, you are building system. So that means you are putting pieces together, like puzzles, right? So you need also to have a very good imagination on how this will happen. That makes sense? Then, tool like, Vivado, right? Vivado, it's just a tool of two things: simulation, emulation. Simulation, emulation. This is something new, you never seen. So you have to observe and learn. Simulation, that means, when you build a circuit using a set of syntax, you have to test it before you will put it on the chip. That makes sense? Like, when you are in the 2300 lab, what do? You put the chip, right? You put like, a decoder of the 7 segment. You put whatever, bunch of OR gates and AND gates and whatever. And then you put wires nearby to each other. Before you go ahead and connect the power supply, right? You have to check that, all of the wires are connecting correct, right? This is the simulation. Then you will actually connect the power supply and the digital analyzers and all of these guys to the board, and then you will be able to see whether that, the circuit is doing correct or not. The same thing. So there is a set of syntax you never seen, and you're gonna learn it here. Those are used for describing the circuit. There is another set of syntax will be used for simulation. There is another syntax will be connecting whatever you wrote as a circuit into the I/O ports of the chip. Then you will be able to generate a bit stream. Then the bit stream will go in where? on the FPGA chip. Then you will go into the emulation by playing on the switches to see whether that is work or not. So far, Elvis is correct. It's clear. So now I'm gonna open in front of you again Vivado. Vivado. Exactly. You need to go to the syntax and you have to learn the syntax. So far, we learned some of the syntax, right? So we learned something is called module. We learn how to describe the module in 3 different ways, right? Structure model, behavior model, and what? Data flow. Everybody agree with me? Structure
Yes.
model, behavior model, data flow. Behavior model, like you are writing C. But of course, performance will not be great. Okay? Structure model, it's basically you are using the gate level. Like, you know something is called AND and OR and XOR, right? So you build a circuit. AND nearby OR and whatever his multiplexer. OR and whatever gonna be AND gate and so on, right? So that means, you're gonna visit back the digital logic and you will go build it with a bunch of gates. So far so good. The data flow is bunch of assignments you're gonna use. It's called concurrent statement. So like, you use some logic operators like AND and OR and XOR as I did before with assign. And pretty much you are assigning something into wire. You don't assign into register, okay? There is something in the language, it's called data type. How many data types so far we learn? We learn reg and wire. Reg and wire. Wire is just a wire. Reg is acting later on that you're gonna store some data. It's like representing something gonna be stored. When we say stored, that means it's gonna be what? Something like a sequential circuit. Do you remember sequential circuit? In a sequential circuit, you store data. Do you agree? Like a flip-flop. How do you store data in a flip-flop? Somebody tell me. Hello?
It just maintains values. If you don't, if the certain selection isn't changed, it's able to maintain them for however long you'd like.
Exactly. So example. So the flip-flop is a device, right? It has a clock. So every edge of the clock you are targeting, the input will be the output. That's one of the flip-flop, right? Which is the D flip-flop. Do you agree? So the time that you will see the edge again, that's a period of time. So that means that period of time you are storing the data. That means the output will not change. Unless the new edge will come, then the data will be accordingly output, it will be the input, right? Unless you have also load signal, like an extra signal, say that if it's high, then you will push data or not. Then you can store more data as much as you can. So you are basically putting the time aspect dimension into your circuit perspective. That makes sense? We can do it. It's not a problem. We're here for learning. I want you to be expert in this language. It is very important to me that to be expert in this language. Why 99% of the industry are looking for this language as a very important language for building products, like robotic stuff, computation stuff, control stuff, whatever you can imagine. That makes sense? I am 100% sure, Professor. Is the lab due is upcoming Wednesday? Yes, Eduardo. So I'm gonna make something in front of everybody again in Vivado. Then I will describe to you this lab as an exception thing. Then I want you to also to grow a certain skill. It might not mature enough, but we're gonna work on how to make it mature enough for everybody. And then I'm 100% sure everybody will be expert. Okay. So let me just first share with you the screen, and I want to show you something.
Professor?
Yes, sir.
In the labs in the upcoming weeks, will you always be submitting them on the Sunday before? Or like releasing it?
You submit.
Yeah, because like we didn't really have time to prepare for the lab. It's only like.
I cannot hear very well. Khalid, can you get closer to your mic? Hello? Khalid?
Yes, yes.
So what did you say?
I said, like we didn't have enough time. You know, it was like only one day. It's I mean, like 2 days. It's just a little bit tight. You know.
Because the circuit is very small, by the way. This lab is the most easy one.
No, I'm talking about like for future labs, we would maybe need more time.
For the future lab, you're gonna have maybe sometime 2 weeks. Sometime you can have a whole week. Sometimes you can have 3 or 4 days. It depends on the complexity of the assignment. So this assignment is not that really complex. This assignment is just learning 2 things: how to put 2 things together, and then it will work. The lab information, Daniel, it will be under the course document. You will find there is a folder called, it's a video. So basically, instead of writing you documents and then, you know, you will have a lot of miscommunication, it's a video with something on the board is working. So that means it's working. And, you know, you will try to build the skill which I want you to build. What a skill I want you to build. I want you to imagine what type of circuit can do this. Then you will put the circuit on the document. Then you will start building the pieces of the circuit on the Vivado RTL side, and then you will build the test bench. So this is very important. And there are 2 ways of designing. Okay, everybody? What is these 2 ways? One will write you a writing up assignment, or basically a specification of a certain circuit. The other one, he will tell you, I want you to build something similar. So my way of teaching is going to be the following. I will make first a couple of assignments based on, you know, look at this. I want something similar. So you will start think of how to build the stuff in a system. Then later on, I will come and tell you, okay, here is a video with a written assignment. Then you will start connecting between of them. We will end up what? With written specifications end of the game. So by this way, you're going to learn over the time how to cover different way of way of thinking. Let me just one second. Let me call you back, okay? I'm in the lecture. Bye-bye. No, you're fine. Bye. Super. So anyway, let's go back into the point. So everybody know, you know, can I ask a question? Everybody here in this class so far have Vivado on his computer running?
Yes.
Super. Elvis? Oh, what happened with Danash? You know, you said no, and Daniel said not yet. What is the problem? Somebody tell me what is, you know, for the people said no, what is the problem? Is there a problem in how to install it, or maybe the computer is not strong enough, or there is no space, or what? Tell me.
I've installed it twice, and each time I end up installing the wrong edition. The first time I ended up installing the installer, which was like, or the update, which was like 40 gigabytes. And then the second time I installed the HSL edition, which asked me for a license key.
No. You don't need to go for the license one. There is one that's called Webpack. It's for students version.
Okay, and the Webpack itself would grant me access. Okay.
Let me see. How can I? Let me see. How can I do that? So actually, you know, look at this now. I'm sharing with you something. You know, I'm doing another work with different tool for FPGA. It's called Libro. It's a micro semi. It's a different FPGA. It's not Vivado. And it is something over time you're gonna learn. It's really cool. So let me see. Sorry, guys. So here, Vivado for students, right? It's called Webpack. Can you see my screen? Can you tell me how can I say your name in a correct way, please?
Yeah, I see a screen. My name is Danush.
Danush, okay. So Danush, you know, can you tell me whether that's, you know, you see it?
Yeah, I see it.
Okay. So I want you to follow. It doesn't run in the app. It does run as an application. It is an application. It's not app. So you know, Danush, you know, you are you have Windows 10, right?
Yes, sir.
Okay. So which version? 64 or 32?
64.
64. Okay. So which version for you, Chad, you use?
Can you repeat that again?
You know, I'm talking to Chad. So Chad,
That's the 2019.1 Webpack.
yeah,
And that
I mean,
works for me.
that's perfect fine. Yes, exactly. You know, I'm using the older version. I have license, by the way, but you know, I got it from Xilinx to support my research. But the problem with this, you know, you guys outside the university, and I believe none of you have VPN, right?
Some maybe, but not all of us.
Yeah, so that VPN story is a little bit difficult to maintain because, you know, how it works, like I'm gonna have a server in my office and then you guys will be it's a big mess. So I don't want you to get into this big problem. So I would say that, you know, okay, Danush, you know, please cooperate with Shad. He might help you with this. Shad, you know, it works fine with you, right?
Yeah, it works well. I downloaded the 2020 version and it didn't work, and then I tried this and it worked.
Yeah, the 2020, you know, the 2020 is basically need license.
Yeah, that's what it looked like.
Okay, so Shad, you know, can you please share with everybody on the Slack, how did you run it?
Yeah, I can.
And that would be really great. For those people who actually succeeded on making it work, can you please help your colleagues through Slack of fixing these issues?
Of course.
Thank you, Mario. Thank you, Shad. Thank you, everybody. So now we will go back into what Vivado. So now I'm in Vivado, right? I'm sorry. Alvis, pay attention. The rest of the people, okay? When you know you would like to do anything on Vivado, first of all, you have to do what? You have to create a project. So like, you know, when you come into the lab in the 2300, what do? Basically, you bring the breadboard, right? And you bring the items with you and you put it on the side and you start putting them, stick them into this little bitty holes, and you know, you will be able to do the work, right? Let me shut the phone so we'll be sure that, you know, nobody's bothering us. Okay, so now everybody see my quick start screen. Do you agree? Okay.
Yes, we see it.
Yes. So create project. When I say create a project, I have to put in my mind what exactly I need to do. What exactly I need to do. What does it mean? It means the following. I have to give a name to my project. Before you just have a board and you just like, you know, stick stuff and you finish your remote, you unplug them and you put it back, right? Here is more organized. Here is more software level. So, you know, I call it here a name. Like let's say today counter, just an example, right? Then you have to have a specific location on your hard drive to collect all of this lab work under it. So basically for me, I make it 5300 course full, whatever 2020, whatever, right? And then you push next. What we are learning here in this class is called RTL. If you don't know what is RTL, please visit the first patch of slides I shared with you before. It has terminology of this course. Do you agree? And you will find it on the first couple of the lectures recorded under the course document. Super good. And then, you know, those rest of the stuff option, like, you know, post-synthesis project, this is something for the advanced FPGA work is called dynamic reconfiguration. It's way far, it is PhD level. IO planning project, that's also PhD level. Imported project, that's something from the older version of the software before Vivado, which is called ISE, and I think you guys are not in need of it. Example project, that's another template which you don't need at the moment. So the only one you put it in your mind is called RTL project. Then, you know, you leave it, don't specify source at this time because you're gonna write your code later. Next. Now, I have to do work. And later on in my mind, I have to plan this work to be deployed on a certain chip. Do you agree? So in that case, this course is supported by which board do we have? Nexus 4 DDR or the Nexus A7? Everybody agree? So in that case, Nexus 4, for me, I don't have A7. No, I think I have A7 somewhere. Yeah, I have A7 here. No, that's microchip. I have A7 somewhere here. Anyway, they are not a big difference. But anyway, if you go in the search in internet, right? Like go into here in internet and just write here, Nexus for DDR XDC. What is the name of the chip on it? I have no idea. One of the way to do it is in the back of your what? Somebody tell me. It's in the back of your what? Of your board or in the website, as you can see, right? So look at this. We are looking for something that's called FPGA part number. And this FPGA part number, we going now to spell it inside the Vivado. What does it mean? Whatever work we're gonna do, end of the day, gonna be deployed in this certain chip. That's ABC. Everybody agree with me? Everybody on the same level of what we are talking about now? If yes, we're gonna go here and say, okay, so look at the message, please. New project. Choose a default Xilinx part or a board on your project. This can be changed later. Okay. So now I'm searching for the same chip part I have here. So the part here is called what? It's called XC7A100T. So let's take this first one like this and take it a copy and put it here. It downsize our search into what? A certain number of chips we can actually use, right? Then if I lift like this back, you will find here -1 and something. What is this -1? What is project time? Oh, it's RTL, okay? Anyway, so now the second part of this FPGA part is called -1. We will leave it. We will leave it, right? For now. The third part here, C whatever, that's called packaging number. It's a package. What does package mean? Normally when they build that chip is three pieces, okay? First piece is called die. That die is basically the whole silicon thing the FPGA is created on it. Then that will be wrapped up with some package. The package is the ceramic thing that you can see, that black thing. Do you see this black square? That's called package. And it has a name. It's a technology. That's name of it is called CS whatever. So I'm gonna take a copy of it like this and go back here to put it nearby. So we found CSG here. So now in front of me, I downsized my search into some levels here, -3, -2, -2L, -1. So now we hit back and visit the -1 we have, and this is basically the -1 we have. So we downsize up to 1, 2, 3, 4, and we picked the -1 because we have a -1. What does -1 actually stand for? Is the speed of the die on the chip. Is it important for you to know what is the speed? At the moment, no. But it's important for you to know that you need it to be by the end of the name of the chip part. That makes sense? Now, I selected. I know my resources, and I already mentioned this in the last video, so please visit the last video that I already shared with you on the Blackboard. You will find a very full definitions of all of single column inside this chip. Like, you know, IO pin count is 324, available IO ports 210, number of lookup table and stuff like that. Now we say next. So look, it says that you already created a new project, and this new project, it has default part, and this default part exactly the same as, exactly the same as what somebody tell me, as one we have in where on the official Digilent website. And it's Arctic 7, the package C, it's whatever CSG to 324, and the speed grade is -1. And I say finish. Everybody here can agree with me that we created a project?
Yeah.
Okay. I want to hear from everybody literally saying yes or no in the Zoom chat, whether that, you know, the steps I mentioned, and I mentioned several times before, is completely clear. Alvis? Actually, very good question. So yes, okay. Elvis, no, I'm talking to Ashley. I'm sorry. Ashley, that's a very smart question. So my boat doesn't light up. That's a different story. So 1 second. So I need to reply back to a question that have been asked. So for you, Ashley, you have to know that every single chip, it has a speed. So for instance, and this speed is belong to the board. Okay. So the chip we have on the Nexus 4 DDR is -1. That means just one speed. That means there is no way for you to use -3, for instance, and it will not fit into the board we have. So it's something static for us, dynamically for them. Yes, Dennis, yes, you can do this, yes. Exactly. I can tell you everything now. Okay, anyway, so everybody will look into my screen in the project summary. You will find in the synthesis saying that the part, and it spelled it for you that you're gonna use this thing, right? And no errors, no warnings, because we haven't stopped anything. So now we have the breadboard. So our breadboard in the 2300 is there. Everybody agree with me? Okay. Now I want to go ahead and say that I want to design a circuit, or I want to build a certain whatever, right? So let's think about what I need to build. Before I do anything, I have to call the IO mapping system in the board. IO mapping system. What is this IO mapping system? It means that here is the chip, right? Surrounded by, did you see this little itty bitty tiny pins in the back here, right? Those are the IO. Pins are IO. What does it mean? IO input or output? Example for input and output. What is the example of input or output? Somebody give me an example. Switches. Switches are input or output?
Switches are inputs.
Thank you. LEDs are output or input?
Outputs.
Exactly. Ethernet, input or output?
An input.
An output.
Well,
Ethernet, right?
I'm thinking of Ethernet cable.
VGA, input or output?
It's an output from the computer.
It is output, exactly. USB, input or output?
Input.
An output.
Input,
Oh,
output.
input.
SD card, input or output?
Input.
An output.
Oh, okay.
He's the SD card. Did you see that? Can you see it in my screen?
Yep.
That's a spot for the SD card. And also I have a kind of something. It's called Digilin gadget. Have you seen it before? Those called gadget. That means you connect it into the specific place here. It's called PMOD, and that will act as it should be as a UART, or can be act as a different primitives you can imagine. Okay. Now, to
Professor,
prepare my thing,
do we need to get those parts that you just said?
Huh?
The ones you just showed us. Do we need to get those parts?
I cannot hear you, Tristan. So what's it?
Do we need to get those parts, the one you just mentioned?
No. I mean, later on, if we need it, I will tell you. If we don't need it, we don't need it, right? I'm just telling you it's an expansion, basically. Anyway, now there is a multiple way for reaching to the chip, right? How can we do this? It's based on the IP. That means something have been already written by the FPGA team in Xilinx, or you will package an IP. That means you build an IP and you will put it there in the catalog, or you will be able to write an HDL describing your circuit. What we are learning so far here is writing our HDL for describing a circuit. Later, maybe by end of this course, I'll see how far people actually expect getting the knowledge in their brain. I can push more beyond the level of entry of the Verilog. So normally I go here. Do you see my cursor? I say add source. There are 3 different categories of adding source. What is the three different categories? It's called add or create constraints. Let's say add or create design source, or say add or create simulation. So how many we have? Constraint, design, simulation. What is those? Constraint, that mean at the end of the day, who is gonna communicate with the board in actual life? Input, output ports. Design, that means the circuit I'm gonna build. And the third, simulation, I'm gonna simulate the whatever I wrote in the design before I will go into the board. So I have three, right? I have what? Create constraint. This is something is not written by us. It's basically XDC file. I have to just call it there. Exactly. So Anish, constraint is the IO. So, did you remember when we said, this chip is surrounded by pins? So what does these pins are? Basically the PCB, when people, in Digilin took the chip from Xilinx and make the PCB around it, right? They came out into a ports, and these ports are like PMODs, switches, LEDs, USB and whatever, right? So they are giving you a map, and this map, how can you communicate to them? How can you push data in and out to them? So you need a constraint file. Okay, so I'm gonna write the constraint file. No, I have to go into the chat in here and say that I want the XDC file of it. So look, I'm searching for my XDC file. I found it here in GitHub. Everybody in the world now putting his work in GitHub. What you say also applies to Nexus. Okay, I mean, forget about it. I mean, I don't have it A7 now, but it's A7, XDC. You search, right? Is this the one you have? So here, you take a copy of it, right? That's a Google work. So basically you go here and say that, copy like this. Copy like that, and then I will go here and just and I say add or create constraint. We don't have one at the moment, so we're gonna create, and we call it any name you want. So gonna be Nexus or DDR. I'm just calling it like that, and then I say finish. When I say finish, I see that number 1 is written here. That means I just have one have been created, right? I go there and I click on it, and then from there I can have an blanked empty file. If I go here and I say Control V, that means I took a copy and I saved it already from the GitHub account. This file have all of the info about how to reach the chips inside your board, right? So now you have some knowledge you need to learn in XDC. It's written in a language, it's called TCO. I call it Tickle script. So it's called Tickle script.
So Professor, for Nexus 4 DDR, that one, it just stays the same? We don't change anything in it?
Do you have Nexus 4?
I think so, yeah.
If you have Nexus 4, you will do the same. If you have Nexus 7, A7, you will go in Google and write Nexus 7, Nexus A7 XDC. You will find that thing, you will copy there and it will work.
Okay, so I just copy it and don't change anything.
Can you constrain? Can you look at the recorded video? I mean, I will do it just one time, okay? I will delete it. We don't need it, okay? Now, add source. So I said add source. How many things I have? Add or create constraint, add or create design source, add or create simulation. So I'm going in add or create what? Constraint. Here. Now, do you have a file or not? I said remove, right? But I didn't remove it from the local drive, by the way. I remove it just from the project. So I can just go and say add file in that case. And that was under here. We said counter. And then, we can go into the source. And then we have the constraint, new. Here is the file. I just created, by the way. If I stop here, you click on it, you will find everything is written as I did, because I created. If you want to create it from the beginning, I would recommend you to watch the video, as I actually shared it multiple times. Anyway, now let's have a scan about what is written inside this file, right? So here, if you want to write anything inside this file and you want it to be as a comment, you have to do this. Then you can write here blah 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 blah. Nothing will be actually what compiled when you will go for the synthesize. Make sense? If you want to write anything and the compiler will not see it, you just do this. Whatever, right? Anyway, let's scan it fast. No, slow. Anyway, first of all, the first two lines under clock signals are responsible of giving or connecting you to what? To the clock generator or this crystal on the chip. That's called internal clock generator. What's called again? Internal clock generator. Those two lines, you have to what? Uncommented them if you would like to have a clock coming out. 1, 2. If I'm connected this, that means, clock 100 megahertz. Did you see this term? Clock 100 megahertz. This one is ready for you to connect it to the design for getting a real clock. So far, so good? Take it as it is. I'm talking about new facts. It's not exist, I'm just telling you now facts. So these facts, that clock 100 megahertz, what does it mean? It means this pin is gonna give me 100 megahertz. If I want lower than 100 megahertz or higher than 100 megahertz, I have to use the video I shared with you before, which is PLL or clock divider. That's something in the digital logic we're gonna learn. Does anyone know how to reset the board? I think I broke mine. Elvis, what did exactly you did? So I can help you maybe? What's the problem? How did you break it? I plug it in and it doesn't light up anymore. Did you buy it as a new one or did you get it from somebody? Did you play with any jumper? Okay. Which class, which lecture you followed? So maybe I can understand what happened, because normally once you turn it on and off, look, I turned it on and off. Look what happened. If it's brand new, it automatically returns it back to the old demo. Look, I just do it like this, right? I just turn it on, off. Did you unplug it? Unplug it and leave it a little bit, unplug it again. You know what I'm saying? Plugging it like this. See, did you hear this? That means the computer will not see it anymore. And I will just connect it like this. Then see what happened? If you turn it back to that. Maybe the cable need to be replaced. That's for sure, Elvis. It's a cable problem. It's cable. If it doesn't give you sound, yes.
Oh, no, I don't want to interrupt you. Sorry.
No, please, Mario. Go ahead.
I was just wondering, out of the XCC file, is all the pins, especially maybe the LEDs and stuff, but I know there's a couple other features. Are they all activated at a logic high? Or some logic low voltage?
Yeah, all of them low voltage. Low voltage.
Wait, they're all low voltage to activate?
Yeah.
So,
low power, yeah.
Oh, okay.
Okay, so Elvis, I believe that you need to change the cord. Do you remember this USB cord you have? Try a different one. I tried another cable, it didn't work. Interesting. I don't know. Maybe, you know, in an office hour, just like visit and I can see. Or try USB. Yeah, exactly, Ashley. Can you make a video, or maybe when you put it on the Slack, you know, as a community, we can help as you know, all of us are practicing actually on the Slack. That makes sense? If anybody have any problem, please post it on the Slack. So, you know, other people on the groups and myself will be able to see it. So maybe myself and other people also will learn out of these issues, right? It's not working, Elvis? What was the reason? I moved somewhat. So you moved that. You didn't remove the blue cover thing. You removed the jumper. That's called jumper. So that's, yeah, that jumper is used for configuration. Don't play with stuff like that. Okay? It's for different thing. I will teach you this later on. Anyway, back to the future. So now, you know, as I said, I'm very slow in this course because, you know, this is very essential course. Okay? Look at this, switches. When we have the tag switches here, how many switches on the board do we have? We have 16. Everybody agree with me? Here's our 16 switches we have, right? How I will know which one I'm talking about? Look at the package pin. Do you see this? J15, L16, M13, R15, R17, T18, right? If you go on your board, let me just do this, you will find out that, you know, J15 on the left side representing the first switch, while the V10 is on the top of the last switch from the right here, right? So you know exactly which one is aligned and represented on the board and also on the documents there, right? On the XTC file. Everybody agree? Okay. Now, what is this what is this git port is? So do you remember the module you are building, the top file module you are building? It has input output ports. Those are the ports. So those are the physical switches, and those are the software switches you're building, and you are connecting them to each other. Again, so in the so on the switch, right, on the breadboard, right, when you are building your circuit, right, you get the switches end of the day, right, and you take wires and you will connect it to the pins on the chip, right, and then you will connect these switches into the voltage, and then you will start on and off switches, right? Same thing. You know, I build a circuit, there is in and out, I take wires, I connect it into this J15, blah, 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 whatever, and then, you know, automatically are connected to switches. Same thing. This is the Verilog, and this is the physical. LED, same thing. You will find also H17 written in the top of the, in the bottom of the first LED here, right? While in the end, you're gonna have V11, which is there, right? Then, you know, the physical, this is the physical, and this is the software. So, you know, beginning with the package pin, that's the physical, and you're ending with the gate port, which is the software, right? Now, 7-segment display. That is gonna be a very important, and we have to move forward towards 7-segment display to be speeding up a little bit. That's have, like, you know, how did you work with 7-segment display in the 2300? You have the decoder, right? You connect it to the, you connected the decoder into the 7-segment display, and from there you're starting connecting ports to change or making counters or whatever. Do you agree? Here, we're gonna build our decoder. So we're gonna build the decoder, customized decoder using the Verilog to communicate with the 7-segment display. So what you have here, we have here a bunch of the cathodes for the portions of the 7-seg, and then, you know, we have here for the point on the 7-seg, And if you notice how many 7 segments we have, 1, 2, 3, 4, 5, 6, 7, 8. Do you agree? We have how many? We have 8. So if you notice in a very little bit tiny there's a dot. This dot represented by the DP, while the AN is representing whether this 7 sig will be on and off. Since we have 8, look, 1, 2, 3, 4, 5, 6, 7, 8. We're gonna read the manual together and we will move forward to implement. Then how many buttons we have on the board? We have one, it's very clear, it's called CPU reset. Can you guys see it? It's reddish one. It's like look like a red. Everybody have the board and can look at it, right?
Yeah.
Okay.
Yes.
And then we have one, it's called probe. That one, it's hardwired, it's not on the board, on the XDC, but it's something else, And then you already have how many other switches? You have 5 switches, which is the one making a cross. You see this? Every one, it has also his name, and you can also align with the physical or the software switch. Then you have something is called PMOD headers, right? How many PMOD we have? Everybody can look, right? You have here 1, 2, 3, 4, 5. We have 3 in a side and a 2 in the other side. So 1, 2, 3, 4, 5. If you notice, there is one of them exceptional. It's called JXADC or XADC, right? This one, it has a capability to work as an analog to digital converter. Okay, one of them can act as analog to digital. What does it mean? That means you can bring analog circuit, it push signal inside the PMOD, and it will be digitized. You can present it, for instance, on a 7-segment display. Okay? All of this we're gonna learn. Now, how can you communicate with VGA? Here is the proper thing. How can you communicate with a micro SD? This is a proper thing. How can you communicate with internal chip for the accelerometer? And also, how can you communicate with the temperature sensors? Everybody has a board in his hand, right? So in a far right, there is something written in the white. It's called temp sensor. This little chip will be communicated by those guys' ports. And we're gonna learn one of the serial communication protocol for this. Then you have here omnidirectional microphone if you would like to communicate with a microphone on a board. And then you already have here the PWM. How many of you heard about PWM?
Yes.
What is PWM for?
It has something to do with the duty cycle, and it's
exactly. It's actually control. It's pulse. Yes.
Yeah.
You're right. So pulse width modulation.
Yep.
It's very important for robotics and control purposes. Yes. Yes, sure. You're right. Then the JTAG itself, it has something that's called AFT or FT chip in the back here. So if you look in the back, everybody have the board in his hand, right? My glasses is not doing really great. Maybe I should wear my reading. 1 second. Stay. So you have here FTDI. See in the back? Navigate, there is a chip here, it's called FTDI. That's FTDI is helping you to work as a USB RST23, which has UART. So we're gonna learn the asynchronized communication protocol, it's called UART. Then if you would like, for instance, to have a mouse connected to the USB, and then you will have like a little computer using FPGA, that's not bad. And then, this is communication for the Ethernet. And here is the thing which is allowing you every time to turn off and on the board, and you will find the board having all the stuff that Digilent has. That's called quad SPI flash. If you flash it permanently, yes, in a permanent way, then you will lose the demo that what's called Digilent is offering, and you will alter it with yours. to close this part of XDC so we will not visit it again. Is there any question so far?
Professor, quick question. So once we do enable one of these in, like something that we're trying to use, how do we refer to it again in our code?
Well, what do you mean? But you know, you enable those and you need to refer, right? So
Yeah, so for example,
do you remember when we said here is this the physical and here is the software? Right. Physical, you cannot touch, right? This is basically what you're gonna use in your what? In your software, in your code.
Okay, so once we enable these in, it instantiates it, so
Yes.
we can access
So
it.
the name in the port, the name of the port on your RTL, it has to be following the same name here, or you vice versa.
Can I change the name of it here?
Yeah, you change it, but then it has to be the same name on the RTL.
Okay.
I'm gonna, you know, you should follow all the lectures I made. It would be very clear, but you know, let's assume that you know you didn't look at it. You know, we're gonna make some example now, and I want everybody to pay attention, please, for this, as it's very essential. Please. Okay, now we covered the clock and the rest of the stuff. So I'm gonna return it back like this. Last lecture, how many of you watched?
We were all there, no?
Huh? You watched, right? So you guys watched the logic analyzer?
Yeah.
Why I'm actually telling you logic analyzer? Because you know we are in a pandemic. We are not in the lab, right? So end of the day, this is extra feature that FPGA is giving us to help us to see what is going on inside debugging without actually spending extra money for having external logic analyzer. Do you guys agree? So we are using extra feature that, you know, Xilinx is giving us, which is also can help us later on to actually convert the whole FPGA into a logic analyzer. And then, you know, you can carry it with you to any class and, you know, using it. Would you imagine? That's really fun, right? So at least, you know, you paid money for the board, you finished 3300 or whatever other courses belong to it, and also you can use it as a logic analyzer for the rest of the classes. Make sense? So anyway, now I'm gonna make a story. So what is the story I would like to do? The story, I'm gonna build a circuit sequential, right? Using whatever we learn in syntax perspective. So what we learned so far in the syntax perspective, we learned the gate's name in the structure level. Everybody agree? We learn how to build a module and instantiate that module into a bigger module. Everybody agree?
Yes.
We learn how to make a parameters for the module. Everybody also agree? And we learn also how to write a test bench, checking and verifying whether this code is written correct and giving me what I'm expected or not. Do you agree?
Mm-hmm.
Okay, so now we're gonna do the same thing, but for a different thing. So now I'm saying add source and create a design. So you have to design before you simulate, right? You have to design something. Now we are not having in Friars or, you know, Fry's or Micro Center to go and buy the chips. So we are designing it. So now we say add or create design source. So I'm going here, add and create design source. I don't have any source with me now. I would like to write it. So I would say create. What language we are using in this course? You can have varieties. You can use Verilog, Verilog header, system Verilog, VHDL, or memory files. In our case, it's Verilog. So what does it mean? The module will have an extension .v. Also, everybody agree with that? So here I would say file name, and that file name I will call it, for instance, let's build something fun, which is basically counter. It's a reason to build a counter. I will show you why. So here counter. Then I will say finish. It pop out to me what type of input output ports you want. That's also what we learn in the beginning of any of the beginning of this course. That means any module I'm building, it has input and output signals, right? The signals we call it ports. And since it's a counter, so what I'm expecting in my head this counter will look like, it should have what? Tell me, if you build a counter based on your knowledge of 2300, what you need?
Clock.
You need clock. Thank you. So you need a clock. What else? It's a counter. So that means it needs what? Huh?
A reset?
Reset. Thank you, Mario. So I call it RST. That's my way of naming stuff. What else in the counter we should have from your point of view? Lois, I'm sorry. Okay. If we use JK, that's fine. Or we can, if it uses JK flip-flop, yes, it will correct. First of all, how are we gonna reach this counter? Using behavior model or structure model or data flow? That's one of the questions we need to ask ourselves about. So what I'm gonna do in this example, I'm gonna use the behavior model, as I played a lot with the structure modeling in front of you. Yes, exactly. So we have two different type of blocks. We call them procedure blocks. Everybody agree? One of them we use heavily in the test bench, what was called initial block, right? That's something we are learning. It's not written before, you know. You didn't take it in 2300. You're learning it here. So that's called initial block. That initial block is basically a block allowing you to state timing, and whether this time happens, something will happen. So start from 0 time up to the certain time you are setting up. Whether this initial block very good in RTL or not, it's not good for RTL. It's good for simulation. The other procedure block we have is called what? Always block. Exactly, as Rtl said. So the always block, it's a block we're gonna use for stating every single time, in our case as sequential circuit, the positive edge of the clock will happen. We will test what is going inside this always block will happen as an updated basically. So let's move forward. So what else in the counters we need to make a counter? I'm talking about the package from outside. I'm not talking about inside now. So you have a clock as an input, you have reset as an input, what else?
You also need your output.
Exactly, you need also an output. So now we're gonna use an output. Let's call it count, right? Do you need anything else to control the counter? If you want to pause the counter, do you need anything? If you want to resume the counter after a certain time, do you need anything?
If you would like to, you could
Yeah.
add additional inputs that could have a say in that.
Exactly. That's Mario, right? So Mario, you're right. So I prefer to have a control in my counter. I don't like my counter to be crazy, like boom, running like this, you know. So I'm gonna make it what? I'm gonna call it here, for instance, you know, start, pause, right? Okay. Now we need to look into the size of every signal, right? Clock, it's just a wire. Do you agree? Reset, it's just a wire. So one bit, basically one wire. Count, I would like to make it what? Parameterized. So every time I will change the size. Do you agree? So in that case, I can make it like bus. Stop and pause, it's just a wire, right? And I can just say like this. Do you guys like also to insert data inside the counter? We can do this later. But you know, for now, here we go. So you notice something there in the source side, it's say updating. So I go into the counter and I open, right? What did I find there? I find that, you know, it's have been created in front of me. What is input, what is output? You guys agree? How I'm going to make it parameterized? It's basically easy. This is also something you need to learn, which is like this. We have local param and parameters. We said we're gonna make it what? Dynamic, so gonna be parameter. And the parameter, we can call it size. And initially we'll give it a value, which is gonna be, let's make it, I don't know, let's make it 4. So far so good? So this is the way in the syntax you can add in the top of the module is called counter parameters for size. Everybody agree? Now, clock and reset, right? In the bus, anybody have a bus in the general, right? That count is basically size. That means from bit 0 to bit something, right? So that means, you know, I need to say that count, it will be from 0 to what?
Let's make 0 to 10.
Size minus 1.
%. Yes, you're right. Size. Why I'm doing this? You need to visit the. Why is the size 4? Because I decided to make it 4. So that's like initial value. You know what? I can make it 8. When 8 happens, that means, you know, count, it will be 7 to 0, which is 8's location, right? 0, 1, 2, 3, 4, 5, 6, 7. If I would like to make it instead of this 5, right? So that means this count will be sized as a 0, 1, 2, 3, 4. 5 here, right? If I make it 4, so that means, okay. So gonna be 4, so that means it's gonna be 0, 1, 2, 3. So Elvis, you know, the parameter, it has to have some default values. So that values, I just put it 4, okay? Now, I have the skeleton of input output, like you make a black box, right? What is in, what is out of this black box. But I didn't say what is inside the black box. Everybody agree? To say what is inside the black box, I'm gonna do the following. All right, so we said we're gonna use what? Always procedure, right, Rahat? So that's basically what we said. So we're gonna say always. Why it is called always? This is syntax. Always at, and you open like this, and you say begin. Yes, what I say? Why? All right. So the output count can range from 0 to 3. No, that's not true. The output will be 2 power of whatever we have. So, you know, if the size is equal 4, right? That's actually 2300. So that means how many bits this count will be? The size of the bus will be 0 to 3. You agree? So that means if it's 0 to 3, so you can start in the 4 location equal 0 to 4 location equal 1111. So that means 0 to 15. Okay? Anyway, we made the always block. And I'm gonna make it a named here and say, you know, up count.
So Professor?
Yes, sir.
When we do behavior modeling, we can't use the assign equals, right? And use those operators, or can we?
I'm gonna do all the scenarios now, so don't worry. Anyway, now I always block. What is exactly in a sequential circuit? That's a question for Elvis. You know, in sequential circuit, what is the most important signal we have? What is the most input we have? And based on this input, the whole entire circuit will be working.
Clock.
I said for Elvis, not you.
Lo siento, amigo.
My goodness. So Elvis, it's gonna be clock. Why clock? It's not giving them. The clock is actually giving you the chances for passing the positive edge or the negative edge of the clock. So the clock work on the edges, it doesn't work on the level. If you guys remember the clock, how the clock looked like, you already have like a edge, level, edge, level, edge, level.
Bunch of rectangles.
Huh? It's exactly like a train of pulses.
Yeah.
Right? So how many levels do we have in the clock? We have high, low, right? And then you back high, low, high, low, high, low, right? And how can you go in the edges is basically you are going from the low to the high. We call this rising edge or the positive edge. And you're going from the high to the low, that's called what? Falling edge or the negative edge of the clock. Syntax wise, how I'm gonna write it? I'm gonna go inside here as this is the sensitivity list. Every single changes inside this list, whatever written inside the begin to end will be updated. So I have to write here pause edge like this and say clock. What is this pause edge? That's syntax. We ever seen before? No. Yeah, we saw in the, of course, the course, but we need to learn that there is something called pause edge. So what what is we have here in the edges? In edges, you need to use either pause edge like this or neg edge like that. So possibility, you can write pause edge, or you can remove this pause edge and you write neg edge. So far so good to everybody? So now I'm gonna write pause edge. So what happened here, always block will be checking that every positive edge of the clock, and when it sees this positive edge, I mean flip-flop, I can build a flip-flop if I want. There is no problem to build it, structure it. But behavior is cheaper. I mean, in terms of time and consuming. But of course, you need to learn on building structure, and that can be one of the questions I can ask you to do in the labs, for instance. Okay. Anyway, so now positive edge of the clock. Another thing I need to mention, right? So the reset, how gonna work? We need to see, right? So there is multiple, this is also 2300. So when I say the reset, how many resets we have? We have
one.
No, I mean a type of reset. We have synchronized reset
and asynchronous.
Synchronized reset. We have what? Synchronized reset or asynchronized reset? Elvis, what is the difference between synchronized reset versus asynchronized reset? Chad, what is the difference between the synchronized reset versus asynchronized reset? Exactly. Synchronized is a clock dependent. Asynchronized is not. So what does it mean, clock dependent? So here is the clock. If I'm under the clock, seeing that, if reset high, but I'm under the clock, that means the positive edge will happen. While the reset high, then I reset. That's called synchronized reset. But if no matter, I'm in the level high or low or positive edge or negative edge and the reset high and it resetted, that's called asynchronized reset. That's very 2300. So what I'm gonna write in front of you now, under the clock, so that's what synchronized reset. So if, and I open like this, if is a statement used in Verilog, and you guys has to remember to write it like exactly what we have in front of us. If you write ref statement and one control line, you don't need begin and end, but normally you should use begin and end so you can have several lines under the if statement. So if here, if what? Reset. So if reset equal 1B1. What does it mean?
Hypothetically, if we didn't put the B1, would that work?
Yeah. Right? Did it work? That's a new control system. But I prefer, I'm just giving you this, because you have to speak the language of the compiler, right? I prefer to do it like this. to be sure telling myself that reset is 1 bit. That means 1 wire, single wire.
Yeah.
Do you agree? The other way, which actually I prefer, is not like that. You can just take this one and aside like this and comment it out. And then you will go here and open another parentheses and say that's reset like this. You know what does it mean, what I did now?
Reset is true.
Reset is true, exactly. So you know it's a logical thing, true or false. So
That's true.
yes, okay. So gonna be here, synchronize, I'm sorry, it has to be one word, So I'm calling this block, it's a block responsible on resetting the clock. So now I'm assuming what I'm resetting. I'm resetting the count as an output. So here count is equal to 0. Why I did this? Oh, output here is giving me error. Why? Somebody should remind me why I did a mistake here.
You don't have count.
No, because output is wire. And you cannot use wire. How can you push data as the wire? The output data, it has to be a type of rig.
Yeah.
That's a very good mistake. We should learn out of it. So my question, so far, everybody understood why a rig happened? Why a root rig? Exactly. So normal thing that, you know, if you want it to be wire, as my notation, you should write wire. But then, because it's wire, it gives an error here, because there is no way for you to push data inside wire. One of you guys corrected me before in a test bench. Do you guys remember who actually corrected me? Mario, I believe, right? Mario, Shad, somebody, you know. No matter what, you got, all of you guys are great. Anyway, so now we know here I'm gonna make a trick, because you know it's used for data, storing data, right? Yeah. And you don't need to say input wire because they are wire. So the importance in RTL is to look into the type of the output as much as you can. So now I make a trick. If you notice, all the error disappears. So I want to be very more professional than just writing 0. So what I'm gonna do, I'm gonna say it's it is like this. It is 4, right? Everybody agree?
Professor, what is the D0?
If you remember, if you look to the older lectures, you will find out the representing of data, it can be as a follow. You put the number of bits representing what in the decimal. Then you put D. If you put here B, so that means, you know, you have to write 4 zeros nearby. 1, 2, 3, 4, like this. So that means counter, it has 4 zeros in the 4 wires. If you write it in a hex, so that means I have 4, so basically you're gonna write here 0, because you know every 4 bits represented in the 1 digit of hex.
So D0 is 1 digit of decimal.
Exactly. But represented in how many bits? 4.
4 bits of like binary.
But then, you know, conversion of the radix is gonna be decimal D. So like this.
Okay.
So it's in the decimal, it's 0, but then you know how many bits are used for the decimal is 4 bits. You understand what I'm saying?
Yes.
Chapter 1, number systems in 2300. Sounds good?
Yeah.
Okay, now I will move and say, okay, if reset is not happening, then this counter has to do something. Do you agree? That's a really nice question. So Christian, you know, I think you need to do it by yourself in a hexa. Then, you know, you will be sure that you are not going into above 9, right? Because in the BCD, it's 0 to 9. That's a very good one. Or maybe, you know what, you can make something that's called procedural macro, but that will be in a way advanced version of Verilog. I don't want to complicate stuff now.
But Professor, isn't D0, isn't it like BCD already without the letters?
No, it's not BCD. BCD, that means the digit is 0 to 9. You cannot exceed more than 9, right?
Isn't this 0 to 9?
No, it can be anything. If I want to make my counter counting from 0 to 15.
No, like D0, isn't D0 from 0 to 9 in decimal?
In decimal, 0 to 9, but in general, I can put any number. Here, I can put here, since it's a 4-bit, right? It can be 15. Right?
Okay, so D15 is what now?
That means in the decimal world, there is 15 is written, which is actually need 4 bits to represent.
Okay.
You understand what I'm saying?
Yeah.
Because if you have a 4-bit, right, and you put 1, 1, 1, 1 there, right? What does it mean in decimal?
15.
Exactly. That's basically what is written. You can build one that's called procedural, but I don't want to put it now too much sophisticated stuff for now. It's fancy stuff. But anyway, we can make a BCD counter now if you want. But after I finish this one. Anyway, so let's say, okay, I'm gonna make it 0. Everybody remember this sign? Do you remember the blocking, non-blocking? It's one of the lectures I mentioned, right? Somebody remind me, what is the difference between blocking versus non-blocking?
One is sequential and the other one is parallel.
Exactly.
Right. Yeah.
If you make a parallel inside the sequential, it's gonna be a chaotic thing. So you're gonna have something. Yes, if you have parallels in a sequential circuit, like an always block with positive edge of the clock, you might have something that's called a race condition. What is race condition? It means that two things would like to do something at the same time. Then in a physics, because we are building circuit, do you agree? So the circuit is what physics perspective is circuit will not accept that. It will be like, you know what? Screw you, Muhammad. I will pick my own one to be the one taken over. How many of you heard about the uncertainty principle?
Uncertainty principle?
Yes.
Heard of it.
You heard it where?
There's a very good chance this was from you, actually.
It was for me. Anyway, so uncertainty principle is a physics thing, exactly. So how it works is basically, it is impossible for you to know the electron direction and location at the same time. So either you will know one of those. So the uncertainty happened here that, two of them happen at the same time. In our time scale, they look like they are doing the same thing at the same time. But if you go further down, maybe there is one faster than the other one in a fraction of time you never see. Then automatically the physics will do the rule and it will pick up the answer and it will be like, I don't like this, I like you to pick the other one. Then, it will come and say no, because at the end of the day, there is a fraction of time you will not feel it as human. Okay? That's why, the story of nano, femto, pico, and all these guys, right?
Yeah.
Anyway.
There's a story.
What?
There's a story to those prefixes?
Oh, yeah, there's a lot of stories.
Oh.
If we have time, I can give you a lot of stories.
A lot of history. Okay.
I love stories. Anyway, so I can tell you the story. So you can assume any part of time, right? You can say that, 10 power minus 100 seconds, right? But nobody will believe you unless what? You can record something happen in 10 power minus 100 of second, right? So milliseconds, why does it exist? Because something happened in milliseconds, scientists recorded.
Can they record anything in even like 10 nanoseconds?
They can record. They recorded something in femtoseconds.
Oh wow!
15. Okay. They have a camera they invented in Caltech, which is recording how two particles of sodium going together to make a chemical reaction. That's why they said there is femtosecond.
Wait, so they recorded that, not just simulated it?
They recorded. They built a camera. That's why the guy he built this, he got a Nobel Prize. He was a professor. I think he passed away. His name is Zuhail or something like that. Ahmad Zuhail. He worked in the laser. So, you know, he used a camera using laser, and then, you know, he came into particles, and they found a particle and particle hitting each other and getting the chemical reaction. Anyway, too much stuff. So back to the counter. So now what we have in front of us is a if statement synchronized under the counters, under the clock, saying that this counter will equal 0 if the reset high with a positive edge. Everybody agree? Now we're gonna go back into, if this reset is not happening, how can we spell this in the syntax level? We're gonna say else. Everybody agree? So if this happens, do what? So the reset, it has two values, 1 or 0, right? We said that 1, which is the true, will do this. So that means if 0 happen, something else will be processed, right? So else, I will go here and say begin, and I say here body count. That means this is the body of this counter. Everybody agree? What will happen there? We have a stop and pause, right? So this is the one will be used. So in that case, we can say if is pause, begin, end. What does it mean? If it's stop pause is true, that means it's high, that means this counter will start. Do you agree, guys?
Yes.
Thank you. So start doing what? Counting. Normally, how do you count? You change from 1 to 1 by 1. Count normal counter in any language. Let me do it like this. It's like count equal count plus 1. Do you guys agree? This in C, for instance, right? So it's the same thing because it's a behavior. Just go and say count is equal count plus 1. Did I say what will happen if the start pause will equal 0? Automatically, I didn't say that means this counter will be what floating, will do nothing. Do you agree? So it is the same thing if I leave it like this, or I will just go ahead and say else. And I do it like this. Count equal count. So it's up to me, you know, I can write this else, or I completely remove it, right? You guys agree? This is not 2300. This is programming skills. Because, you know, you have a, you know, how to program, right? It's a flow programming, right? So you already have, if this happened, what will happen? If this happened, what will happen? Branching, right? Finite state machine. So in my case, I can leave it or I can just remove it. I don't need it. So with this current code in front of you guys, what will happen?
Well, if the start and pause signal is at is 1, you'd get a counter that's increasing by 1 at every positive edge of the clock.
Mm-hmm. So let me, Elvis, this code doesn't run parallel, right? What do you mean by running parallel? I mean, the compiler will do it parallel, but, you know, the behavior, it will be sequential for sure, because, you know, you're waiting a reset, you're waiting start and pause and stuff like that, right? Okay, anyway, so now I need to test whether this counter is doing what I'm asking for or not. Everybody agree?
Yes.
So I have to write the third element, which is called synthesis, right? Sorry, not synthesis, I'm sorry. Simulation. You guys agree? So in simulation,
Yeah.
I'll just go ahead and say, add source, add or create simulation source. And I go here and create. And then I say in a Verilog, I say what? I say counter, and then this counter TB. I'm giving a name. So this is a test bench. And I say finish. Normally, what I said about the test bench, somebody remind me, I said the test bench doesn't have what?
No
Input output ports, right? That's something also new. You need to learn, okay? So automatically, I have to look into the source simulation here, and I found counter underscore what? TB. So far, so good. What I need to do now, I have to instantiate that module inside what? Huh? Inside what?
The test bench.
Inside my test bench. Exactly. So now, because I don't, I don't have a very strong memory, I can just counter like this, and I go like this, and I stop here, and move forward, and then I can just go ahead and do it here for a moment, but later on I will clear it up. Everybody agree? And then I would say here counter. I'm just mimicking stuff here, right? What this counter it will be? We need to name it, so maybe I can just say here size. No, I'm sorry. Size. And then I say, let's call it up count. That's the name of it when we instantiate. If you guys remember, how can you instantiate? Later on, maybe I have an error and I will fix it, okay? Now, we're gonna go here and do our job, which is dot clock, dot reset, dot count, dot SPS. You guys agree? Why he's mad? Maybe we can find what's why he's mad. He's mad from something. Maybe we can just do something. Why there's an error? I forgot, maybe there's something I missed. So 1 second. I think it's a syntax, so let me see. 1 second, 1 second. Yeah.
Is it because you put the size as 8?
No, I think I made a mistake. It should be like this as a syntax, and then you name it here. All right, that's it. So normally, if you have a parameters, you say the name of the module, and then followed by the what is the size, and then up count, right? I don't want the size to be like this. I want it to be also kind of connected into the parameter of the test bench, so I can do the same thing. I just say here parameter, and in this parameter I can say counter. I say size underscore TB, and I give it a number and say that 8, for instance, and then there I can say size is equal what? You guys agree? Are you following me?
Yeah.
Okay. Now, the part which I really like, which is basically connecting stuff in and out. We need a clock. We need to make a clock. We need to make a reset. We need to make a count. We need to make many things, right? So inputs inside, it has to be storing data, right? Before in the RTL, it was input register wires, and the output can be register or wire. Everybody agree about that?
Yeah.
Now it's different. Now all the inputs I assume as what? Rig. So I have a clock here, TB, that's a name, and I have a rig reset TB, and rig, and then wire, and they're gonna be size underscore TB -1 to 0, and they're gonna be count underscore TB, and rig is TBS. Sounds good. This one, any output for test bench should be considered while any input of the RTL module should be considered rig for injecting data as you are doing in the lab for passing voltage. Is it clear to everybody? So now I can just put here clock TB, I can put here reset TB, and I can put here count TB, and I put here STPS TB. Sounds good? Are we missing anything? Huh? We are missing what?
Well, we're missing our initial values. Just to
Exactly. We're missing the initial value of the clock, of everything, right? Everybody agrees with me? So in that case, I need to use what? The rule coming here, the time to inject inputs, which we will need in this case to use initial blocks and a proper way of generating clock, right? So, okay, first of all, I need to do what? To generate what? Somebody tell me. To generate a clock. I need something to generate a clock. I'm not gonna take it from the FPGA board, right? Why? Because FPGA is not there, I'm just testing, right? So in that case, I have to find a way to generate a clock. So here, what we can do, I can do it very easy. Let me do it for you. I can make it with initial block, or I can make it with what? With always block with forever. There is something called forever function. So I'm gonna do it for now with initial block, with always block, and then later on I will do it for you forever when the times come to the forever state. That makes sense? So initially, I can say initial begin end, and that will be what? Resetting the clock into, I'm sorry. Initial. That's the name of the block. Why he doesn't like it. That's what in
I think you just need to make the space because it's not showing anything on my end.
Your initial is spelled wrong.
Huh?
You're missing the second or the third I in initial.
Oh, you're right. You're right. I'm sorry. Initial. Thank you. Thank you. Thank you. See, that's actually good. You guys are following. I love that. So basically, I would say that, clock, TV, initially, I like it to be equal 1. Why I make it equal like this without using block and non-blocking? We are in test bench. So it's more software level than, a real actual hardware level. That makes sense? Now I'm gonna use always block. But you guys seen before my always block different, right? You guys saw my always block before with this at and then, you know, some parentheses and stuff. Always block in a test bench, it can be written like always like this. Did you understand? Because, you know, you don't need to look to a signal every time something will change. So in that case, I'm gonna make it with, let's make the clock 100 megahertz. 100 megahertz, if you guys remember from the 2300. 100 megahertz is what, how much nanoseconds? 1 over frequency, right? 1 over 100 megahertz second is what? 10 nanoseconds? 10 nanoseconds. Clock, it's basically the on is equal the off size, and both of them are in times 2. That means, you know, 5 on, 5 off will be the 10 nanosecond. If you flip it, it will be 100 megahertz. Do you guys agree about that? Everybody here? Excuse me. Okay, so here, I'm saying every 5 nanosecond, flip the clock. But there is no clock. We have to stick with the name of the test bench. So what I did here was this 2 segments here, generator clock gen. Here in the beginning, at the T0 of the time, I assigned 1 to the clock. So the clock came like this. Then, you know, I start going like this. Everybody agree?
Yes.
Professor, what's the function of the thing before the clock underscore TV?
Huh? What is this?
You see where there is there's the hashtag 5 and then clock underscore TV.
This one? Yeah.
What does that thing do?
I will tell you. The continuation of the clock. You want this clock to be generated on, off, on, off, on, off, on, off all the time, right? The initial block did it for you just like 1, like this, right? But then how can you continuate on and off? You have to come and say every 5 nanoseconds, the clock will flip itself. So if the clock is 1, after 5 nanoseconds, make it 0. Then after 5 nanoseconds, again, make it 1. Then after 5 nanoseconds, make it 0. Then after 5 nanoseconds, make it 1. That's why I'm using always. That means always generate a clock. Exactly, it's flipping it. Do you remember the sign? Come on, it's from the, it's also from the patch of slides I gave it to you. So that actually make it negated. So basically, you know, every 5 nanosecond, what will happen? What is the value of the clock is 1, right? So now clock, you invert it to not gated, so what, 0. Then, you know, after 5 nanosecond, clock is actually 0. You negate it again, it's gonna be what? 1. After 5 nanosecond, you will negate it again, 5.
And so on.
You know what I mean? Okay, we succeeded now. Is there a way to change the unit of time, millisecond to instead of, yeah, there is a way for sure. But, you know, let's stick a little bit with this, and then later on, I will add you this aspect. You can make it milliseconds, you can make it any numbers, whatever. But, you know, if you want to make it millisecond, you can just write millisecond. Make sense?
I think you probably need another 0.
Yeah, because, you know, those are units coming from other units, right? Which is a second. Anyway, oh, scheiße. Anyway, now we need, are we finished? Or there is something else we need to do?
You still had to give more initial values.
Exactly, initial values to who?
To our reset and to our start and pause.
Exactly. So now we can make another initial block. Elvis, if you notice, everything here is parallel. That means, you know, this will happen in parallel with this, and that will be following this. You understand my point? So gonna be, there is multiple thread happening. So initial begin. So here, you know, skeleton of the counter inputs. So this is the block responsible for the pushing the reset and the STB values, right? So initially, I want my reset, I'm sorry, my reset TB to equal 1. That means I reset in the beginning, right? And we're gonna see something happening, and then we will be back, okay? So now here, I'm saying after how many seconds I would like to see something different happen. Here, STPS TB at the time of the reset is equal 1. Do you care about it?
No.
Everybody agree? You can leave it as it is, or you can put it with a value in the beginning of t equals 0. So in that case, I can say b z. Here. So what does it mean? It means in the t of the time, floated, don't connect. Keep it like this, the trash. Then after 10 nanoseconds, that means after 1 cycle, basically, I would like to change the situation. Change it to what? I can make my reset equal 0. That means no more reset. You can do whatever you want. In that case, if I keep the STB as TBZ, do you think the counter will count? That's one of the corner case. Do you agree?
So if the reset's 1, the counter won't be counting. It's only.
Exactly, but I have a question. Yeah. If it's Z open like this, do you think it will count?
No.
No.
We don't know, right?
Yeah.
Physics will come here, right? It's worth actually to see what will happen. What do you think? Leave it. So, if I don't write anything in Z, so that means actually in after 10 nanoseconds, Z still, the STPS is still Z. Do you agree? Because I didn't update it. So here, initial block is what? Sequential. Have you noticed? Do you guys agree? Because, if I say, for instance, here, after 100 cycle, 100 nanosecond, that means every cycle is taking 10. That means after 10 cycles, I consider reset is equal 0, and it still is TBSZ. Are you guys following me in this part?
Yeah.
Okay, good. Then, now, I can come and say STBS-TB, it should be 1 to operate. Then maybe I know that my size here is 8, right? So 8, that means it's count up to 256. Do you guys agree? So in that case, you can make 256 0 time, and then you can come and say put STPSTB equal 0 to see whether that's gonna stop after that or not. And then you can come and say put 100 cycles more, and then please close the simulation. So I want everybody to understand what I'm doing now. So Lois, is it clear to you?
Yeah.
Okay, Elvis, is it clear to you? Elvis? Okay, so yes, internet shut off for a second. So do you think whatever I wrote in front of you, is it clear? Elvis? So the code I wrote here in the initial block of the skeleton underscore counter underscore INPS, what I said in the beginning, the reset is equal 1. That means, the counter supposed output of it will be what? 0, right? then I'm saying that, you know, while I'm resetting, I don't think I need the STPS to be any value, right? So in that case, I can make it X, like I don't care, or I can make it Z, which is basically like I'm floating it, right? This is a data format. I give it to you guys in the early of this course. Then I'm saying after 10 nanosecond, which is one cycle, the reset will equal 0. But I didn't say anything about STPS. So that means TPS is still Z, right? After that even cycle. Then what is the reason for using the Z for floating the wire? That's not wire, that's a rig. Do you remember when we said in the test bench, you know, the input will be rig? So what I'm saying here, if the reset is synchronized, right? So when the clock is high and the reset happens, everybody agrees with me? Do you think whether that, you know, STPS is equal 1 or 0 or anything, the counter will count? Right? You agree? Do you think Z with any value? Yeah, we don't, I mean, no, you should know. You know, that's a circuit, you know. If the reset is high, that means you're resetting. You understand what I'm saying? So if the reset is high, you know, how you know you're gonna resume counting? Look at the code very well. So here back. So look, if the reset is high, exactly. So that means, you know, it doesn't matter what is the value. Yeah, it doesn't matter what is the value of what is TPS. If it's high, if it's low, if I have no idea, I don't care. Do you agree? So that's why I set it up to Z, because, you know, that means I'm not connecting it at all. Z, that means floated. That means it's just a wire. It doesn't have any values written in it. Okay, so now after this, we moved into the, after 100 nanoseconds, we know the duration of the cycle is 10 nanoseconds. So we are talking about in total 10 cycles, you know, the STP will equal 1. What does it mean? That means in that moment, after 10 cycles, the counter will start doing what? Counting. Then I would like to see how many cycles it will be acting correct. So that's why I put 2,560. Why? Because this counter, we parameterize it to 8 bits. So 8 bit is representing 0 to 255. Do you guys agree? Every cycle will be incrementing 1. So that means I want 2,560 nanoseconds divided by 10. So that means 256 cycles. Then I will stop the counter after that, and I will wait for 100 nanoseconds to see what will happen. And then I close. Let's run, because I think there is an error.
Professor, before you run, can you just scroll up a little bit?
Sure. Where?
Okay, got it. Thank you.
Sure. Anyway, so now I'm gonna simulate and see whether this thing will work or not. Okay. And let's see. So I say simulate, run simulation, and see. Takes some time, sorry about that. It did what? It did simulate, right? So if I open like this, I can see the counter. If I change the radix of the counter, I say here radix unsigned. That means you're not counting, right? So 0, 1, 2, 3, 4. So look in the beginning. Look what happened. Look. First cycle, I make the reset high, right? And I wasn't caring, right? Then I said 10 cycles later, 10 cycles later, I wasn't also caring, right? About, you know, what is Z will be. That's why, you know, the counter stayed as it is. How do you change the increment for the time on the simulation? What do you mean? Oh, that's not really hard. So basically, if you click here and say simulation setup, you go there and you can find an actual simulation. Look here, runtime. That's a good question. That's technical questions in simulation. So it should be fine. So look, normally in default, they give you 1,000 nanoseconds. Oh, weird. So I have to check. What version of Vivado do you have? Or maybe it's different. So maybe you can show it to me later, okay? Now cancel, and then from there I start counting in the moment that STPS went high, right? Everybody agree? You mean zooming into the simulation timeline? Yeah. What do you mean like this? Michael? Did you see the part that Khalid was asking about, why the clock went off and on? See, it's from 10 to 20. That means 10 nanoseconds. 5. Right? And now, this is counting up to 78, up to whatever. But have you noticed it went to 89 and stopped? Why? Because we have to click here and it changed the setting. Because 1,000 nanosecond, we already exceed the 1,000 nanosecond. So we need to put number bigger than that. So 0, 0 maybe. Let's see what will be the values. Yes, discard. And then we can say run behavior. Yes. See what happened when I increase the timeline, it actually exceeds what I want, right? So look, it came into the moment after 2005, whatever, right? Into the moment that the counter, if I go radix, sorry, 255, right? And then I waited for one cycle to be 0. Then I went down into the STPS, so it pretended to be back to be 0. So this counter did exactly what I asked it. So everybody agree? So the counter does exactly what I want. So far, so good.
Professor,
Hello?
can you go back and show me how you go into settings to change that?
Yeah. Click right, simulation setting, and simulation here, runtime. You have elaboration, compilation, simulation here.
Thank you.
Chad, you should actually do this. Do you see the screen in front of you? Because I exceeded the time of simulation. So the time of simulation was 100 nanoseconds, 1,000 nanoseconds. But look how many cycles I have, right? So I was more than that, right? Make sense? You can be tricky. There is no problem, you can just go ahead and let me do something for you, which is a second. I will do something for you very good. Stay with me, I will do something for you. One second. I think you can set up a, let's say you can make you make it like a constant. I need to find you the right one. It's called constant. And from there you can set up the time duration different. But you know, leave it for now. But anyway, now you understand the steps so far, right? So I just want to do one thing before I will show you the thing low during the simulation. Even you are doing the same thing I'm doing, right? Chat. Did you do the same thing like this code? Oh. Look, reset tab is equal 1, 10 nanosecond, it will be 0. So how are you gonna be low? I think could have messed up something. I think so, yeah. Anyway, now it's a time for putting it on the board and see something weird. Make sense? I'm gonna show you something weirder. What is this? Now in front of us, the size is 4, and we are in the RTL itself, no more test bench. And I want this to be deployed here on the board. Okay, so first of all, I have to communicate with who? Somebody tell me. We have to communicate with who? XDC, right? So the software pin of the clock, what is the name of it? CLK. You guys agree? So we're gonna take this name and go into the XDC and find anything belong to the clock and it change the name from the whatever to clock. So how many lines in the XDC belong to the clock? 2. 1, 2. You guys agree? So the name here initially was clock 100 whatever, but in soft in RTL it's called clock. So we have to make it same. So gonna be here clock. Gonna be here clock. So officially, in a virtual level, the RTL clock is already connected to the pin on the board. Later on, we'll deploy. You guys hear me? Hello?
Yes.
Everybody agree? It's not that very hard? Elvis? Okay, now the second one is called reset, right? I want to see what reset I can do. So pretty much what I can do, I can pick one of the buttons out of those 5 buttons to be my reset. So my official reset in here, I will take the P, the B, T, and C, which is the N17. So I have to go into my XDC. I see where is this here. So I'm gonna take this guy and I will replace this word B and TC to be a reset. So that guy, you know, when I will click on it on the board, it will reset the count. Then still I have count. So the count as the size is 4, so that means is the 3 to 0. So that means which device I should use to represent at the moment this counter. Somebody tell me. If I have a counter, and at the moment we learn switches and LED on the board, what should I use as an output device?
The LEDs.
LED, exactly. So here's my LED. So maybe I can take the first 4 from the right? So 1, 2, 3, 4, right? Those called LED, but you know, the thing is called count. So what I can do, I can just go back here and say, instead of LED, count, 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 count. Make sense? Count, count, count. You guys agree? Any question? So now, the last one we need to put into the consideration is the STPS, right? So I can take copy of this and I can assign it to one of those switches. Do you guys agree? So maybe I can take the right one, which is the J15. So if I go in there and I say, where is the switches? J15, this one as a physical. So maybe I can just go here and remove this guy and I put STPS and uncommented this. So far, so good?
Yeah.
Okay. So we agree now that STPS clock have been connected, the outputs connected, and receipt connected. Do we have any other things to connect before we start the synthesis?
No, doesn't.
Not really, exactly. So now it's a time to what? Run all of the passes of generating sync to be deployed on FPGA. So later, we'll be able to see it on the FPGA. And then, we're gonna see some surprises here and we will fix it. So far, so good. So our class until what? Until 2 what?
Until 2:30.
2:30? I think we will leave by 2:15. So you guys already have like a big lecture. So yeah. Maybe double check, I don't know.
Yeah, I thought it ended already.
It should be ended now. Are you tired of my class?
No, I'm not tired of
Yeah, no, he's tired of my no.
I have an exam today. I still didn't study for the whole thing.
No. He doesn't like my class.
I love your class, actually.
Okay. Anybody else like my class so far?
Okay, I heard a very loud but distant no.
No, sorry, that was my family. Forgive me, he's so loud. That's my bad.
That's why it's no problem. Anyway, so the second step of the synthesis is basically implementation. So how it works in FPGA, you write the code, then the library will come into like, oh, I see something like this, oh, I see something like that, and you put it on the side. Implementation is actually connecting pieces. So now I say run implementation. So thank you for you guys for saying that you like my class. Thank you. I know the rest of the people who don't like me. Anyway, so now we say
Extra
that.
credit?
Huh?
Extra credit?
No. Everybody's equal here. Anyway, so initializing design. Excuse me. Takes time, Have you noticed while the synthesis is done, it gives us some info, which is how many lookup table 2, how many flip-flop are 4, right? And the implementation says it is the same thing, 2 and 4. Sometime, which is a rare time, that you will find the implementation giving you different number than the synthesis. No. This bench is completely far from the board. This bench is the step before you will go to the board. Okay, so that this bench, you are sure that whatever you're gonna deploy in the board, it's worth it. Because if you say how much time you are taking to deploy on the board, so that's why that this bench should eliminate errors as much as you can before you will go to the board. That's why you are simulating. That's called verification, RTL verification. So you are verifying your code is fine and is a good candidate to be on the board. That make sense? Implementation went perfectly fine, right? Now I'm saying generating bit stream. Now it's giving me some roughly info about, you know, how much power it takes here, right? Which is 0.109. It's a fraction of watts, right? And it's giving me here some times like slacks and stuff like this that will be covered in some lectures in later. We still have a couple of weeks. You're gonna see a very big surprise. Excuse me. Everything is cleared up, so there is no error. Now we say open hardware, and from there you say open target. You should have the board on, and you should have the board on, and you should have it connected to your computer, to the port. If it's not connected, you know, you'll not be able to identify the hardware. So now look, it's connecting to it. It's considered like a server, and from there it found it actually. See, it's found it. Right? Then now I'm saying it's a time to temporarily remove whatever written by Digilent doing this fancy light up stuff into the new thing, which is a counter. So if you notice, nothing is working, right? Which is cool. But now everything is working, but you know, those 4 output is basically is not blinking as 1 and 2 and 3 and 4 and 5. Somebody give me an idea why. So we have a reset here. Look, when I reset, it turned to be what? Look, it turned to 0 when I reset, right? While, you know, I stop here. Have you noticed when I stop and turn on, stop and turn on, values are changing. So that's something in physics. It's not Verilog. You guys need to know about it. So how many of you heard about something called HVS? Okay, HVS, it's called Human Visual System. So I have a question. Can you guys see virus by your eye? Can you guys see bacteria by your eye? Exactly, it's blinking too fast. If you have your phone, because 100 megahertz, your eye will not recognize. Your eye is slower than 100 megahertz. So if you bring the camera and you make it in a slow motion and you do it like this, you will see this blinking. But how can you see it in a level that, you know, you will recognize it? You have to slow down your counter, which is actually feeding the data between input and output. That's why you need a clock divider. And that will be the next thing that we're gonna talk about next time. Maybe you can look into the video I shared with you about the PLL, but that still will not give you a very good idea because, you know, 10 megahertz still your eyes will not recognize. You have to go in kilohertz. So that does make it sense for you guys?
100%.
So my question, so far, whatever we discussed today, is it clear? Is it clear or crystal clear?
I would say so, yes. It is very much so.
Thank you. I would like to see the opinion of the rest of the people. Before I leave you, because, you know, I know that it's 2:15 end of the class and I don't want to give you too much because you have another, I'm sure that you have other stuff to do the rest of the day. So let's talk about the lab again. So what is the lab? The lab is very easy, right? There is a knowledge we learn from the 2300. That's not circuit. That's not even Rtl, okay? This knowledge say that I have a box. This box, it has 2 inputs and 2 outputs, right? And 2 signals, control signals. One of these control signals will select which of the input will be represented in the output, okay? While the second selector will choose which device or which section will represent that output, right? That's basically the. So what is exactly inside has to be written. That's your job. Is it clear?
Yes.
Rest of the people, is it clear? Alves, is it clear? Sort of. So what is the problem? Maybe you can share with me, and then I can go through it fast. If imagine, what is the thing that it gives you 2 inputs and 1 output? And there is a controller will select which input will be that output. Then there is another one is saying that here's that input, it can be that output or that output. What is the circuit of this? Demultiplexer. Come on. You guys, did you guys take the demultiplexer? So imagine that you have a multiplexer with demultiplexer. What will happen? Okay, anyway, any other question? You guys have any concern or any problem? I would be more than happy to solve it to you before I go. No, you don't need to say you forgot. You're fine. I was concerned about the lab parameters. I need to review. Yes. Christian, yeah. So basically, the lab parameters, that inputs every single side of that input, right? It can be 4 for each. It can be 5 for each. And I believe that we have done this before. You said that there was something about the voltage. This is a PCB board. I'm talking about the voltage in the PCB board. I'm talking about you mean power, it's not voltage. So when I say power, look, where did I find the power? Do you remember? When I was looking here, look, I found the power here. Once you wrote your code, yes. So you need to look at these values while you're writing the code, and don't forget this is structure. You're gonna make everything structured. Any other questions? So if there is no more questions, I would like to thank you guys for attending this course and attending the class today. And I hope everything is getting more and more clear. And I wish in the next other lectures that I'm gonna share with you, they're gonna make it more and more clear. Okay? Thanks so much for your time and your effort. And I appreciate it. I know that it's really quite heavy days, especially with this pandemic for both sides, you and I, but let's do the best, okay? Thanks so much. God bless you guys, okay? Stay safe.
Professor, are you gonna have office hours today?
Calendly, go in Calendly, book a dime, and
because I went on Calendly and like it showed me I couldn't even click on today.
What?
Yeah, I don't know what's happening. Can I schedule a manual appointment?
It should be automatic appointments.
I tried.
We'll see. Just send email and I'll talk to you, okay?
All right.
Okay. Thank you, guys. God bless you. Stay safe. Thank you. At night, I will share with you the recorded video as well. Thank you. Bye.